Um, okay, well, then it's my pleasure to introduce Zahra, who's going to tell us about non-relativistic physics in ADS and its CFT dual. Please.
Thank you, Donald. First, I want to thank all the organizer for organizing this conference and inviting me to speak. That's a very great pleasure. So I will be talking about non-relativistic physics in ADS and its CFT dual. This is based on a work with Henry Maxfield, which is to appear soon. Okay. So the study of the correspondence between ADS spacetime and CFT has started more than 20 years ago. There has been a huge literature on it, but for the purpose of this talk, we define the correspondence to be a duality between the theory of quantum gravity in D+1 asymptotic space-time and a d-dimensional CFT, a d-dimensional local CFT, which is depicted in this picture. So the ADS is depicted by the cylinder, and CFT in the radial quantization is depicted by the sphere. So even though this correspondence has been studied for 20 years, there are much more physical insights and intuition left to be understood about this. So in this direction, we aim to study the duality in the well-known controllable non-relativistic limit. In particular, we focus on some questions which are of interest generally, and we approach them in the non-relativistic limit. One question of the sort is the following: Can we actually understand the CFT scaling dimension and OP spectrum, which are organized in the Regge trajectories in the non-relativistic limit for the CFT with a holographic dual? And the second question I would like to probe in this talk is that whether or not can we understand non-relativistic flat space scattering from the CFT correlator. So this is expected from taking the large radius limit of ADS. So one would intuitively expect that if you take the large radius limit, you would recover flat space-time. And because you recover flat space-time, you might be able to recover flat space-time scattering. And because of the duality, then the flat space-time scattering you recovered should be the same as the CFT correlator. However, there are subtleties and obstruction. Specifically, the main question is how to actually build the in states and out states that give the scattering amplitude, which is dual to correlator. So these questions both have been of much interest in the in different limits and in generic setup. Just to name a few people who have worked on it, especially for the second question, like Polchitsky, Giddings, Gary, Pendos, Kaplan et al. Have all addressed this question in different limits. Because of this, we think that studying this problem in the non-relativistic limit might shed some light on the nature of the duality and help us better understand it. So in order to approach these problems, let's first cover some backgrounds. So the metric of the global ADS is given as follows, where L here is the radius of the ADS. In the global coordinates, we can actually show this space-time as a cylinder, and we can recover the global coordinates from this coordinate by just the coordinate transformation, which I've written here as a tangent of rho is equal RL. So by this transformation, you can actually recover the cylinder. So pictorially for ADS, you can just imagine that you have a cylinder with finite radius and the time evolution is going upward. So we are interested in the non-relativistic dynamics. So we want the spatial part of the velocity to be much less than the temporal part. This would in turn mean that we can actually identify the time component of the metric as follows, where phi is a gravitational potential corresponding to a constant mass density. Here, omega is given in terms of c over L, where c is the radius of, c is the velocity of light, and L is the radius of the ADS. Now, one thing which is important is that this potential confines the dynamics of the NR particles to stay in region that are much smaller than ADS radius. So we are, with the non-relativistic kinematic, we are not able to probe a spatial curvature. And the signs of the curvature, the signs of ADS curvature that we see are through this potential phi equal 1/2 omega squared r squared. Now, with this potential, we can actually write the Hamiltonian of the non-relativistic particles in ADS as follows. So I wrote a 2-particle Hamiltonian, where VR is their interaction. Interestingly, this Hamiltonian, you can also derive it from the full relativistic Hamiltonian with the Laplacian, but taking the non-relativistic limit of the ADS Laplacian. So yeah, everything is consistent. So now that we have covered some background, let's actually approach the problems. In order to approach the problem, first, I would like to study the symmetry of the problem, because by understanding it, we might be able to choose the states that trivializes this symmetry, and this would simplify our life very much. Then I would approach the first problem, which is to find a scattering amplitude from a CFD correlation function. First, we're going to define what a CFD very quickly define what a CFD correlation function is. And then we will see how to prepare the scattering states through Euclidean time evolution. And then we define the flat space amplitude, and we show the equivalence pictorially. As approaching the second question, as a first step, I would like to approach the question, of course, perturbatively. We would like to understand the CFD spectrum from quantum theory in the bulk. That would be interesting if we could do that. At the end, we check the result we get by an actual CFD fully relativistic calculation, and to see that the result that we get for both matches and agrees. And then we have summary and outlook. So let's go to the symmetry of the problem. So symmetry of the problem is, of course, conformal symmetry. We start by studying the symmetry algebra, as I said, in order to find out which representation trivializes them. The symmetry algebra of ADSD plus 1 is SOD, 2, which is spanned by the dilatation operator, momentum operator, special conformal transformation, and rotation, with the following algebra, with the following commutation relation. Of course, along with the SOD algebra of rotation, which I haven't written here, with Ki and Pi transforming like vectors under rotation. Okay. So now from this, we would like to extract the non-relativistic symmetry. One thing to note before doing that is that the dilatation operator in the global coordinate that we just discussed in the cylinder coordinate would just become time translation. So it actually becomes our Hamiltonian. So in the non-relativistic limit for particles of total mass m, this would become rest energy plus the non-relativistic part. This would then help us to simplify the algebra, just assuming that m is much, much bigger than h and r. And this is what we get for the simplified algebra. As you can see, that some part of the commutation dropped, and this is a simpler version. So something which is interesting is that now we can actually express the action of the momentum operator in the global coordinate again to see how it acts on the position and momentum of the particles in the cylinder. We see that the PI operator acts linearly on MXI and PI, so it must act on the center of mass wave function. We also see that this form of PI that we get is very familiar from quantum mechanics. And indeed, it's actually creation operator for a harmonic oscillator if you actually do a rescaling. With that rescaling, we can actually write this algebra as a harmonic oscillator algebra, and we have recovered the algebra of the harmonic oscillator as our symmetry group in the non-relativistic limit. Where here, as I said, the PI and thus AI dagger would act as a creation operator on the center of mass wave function. So from this, we can write the non-relativistic Hamiltonian as a Hamiltonian for harmonic oscillator plus an additional part, which would now, of course, consequently be the relative part, because the first part explains the center of mass. So we find that we can actually trivialize this symmetry by choosing the ground state of the harmonic oscillator, which subsequently mean that we are actually looking at the primary states, because ground state is a state annihilated by AI, and AI is the same as a special conformal transformation. So ground state is a state that annihilated by a special conformal transformation, which is by definition the primary state. So if we focus on the primary state in the center of mass wave function, we have actually trivialized the symmetry. So now we have a simplified problem, which is that the energy shift of the primary two-particle state comes only from the H relative. So if we study the H relative part, we can actually get the non-trivial dynamics. All the non-trivial dynamics goes into the H relative part. So yeah, if you haven't followed the symmetry argument, this is just the takeaway, that the H relative part is what's actually important and dynamical, and the rest we can just constrain with symmetry. And yeah, what matters is the H relative. Okay, so we have covered the symmetry of the problem. We have found out what part of the, what the states we need to consider. So now let's go and try to build the scattering amplitude, which is equivalent to correlation function. The CFT correlation function of 4 scalar primary operators, I chose them because I'm interested in the scattering process. I looked at identical pair of operators, and it's given as follows. So except for this overall prefactor, the correlator only depends on 2 variables z and z bar, which are related to space-time position as follows. And this comes from the conformal symmetry. And in order to go to the non-relativistic limit, we just have to have a large dimension with z times the dimension held fixed. So large dimension and small z at the same time. The operator dimension is actually the eigenvalue of the Hamiltonian, eigenvalue of the dilatation operator, thus the eigenvalue of the Hamiltonian in the cylinder. So it's the leading contribution to it comes from only mass. So sometimes I actually put C, sometimes I don't, but yeah, just that's the way it is. Yeah, now we need to, but now we aim to build a flat space scattering, which gives this correlation function in the non-relativistic limit with this relation between z and delta. Okay, first let's study how you prepare a single particle state. Then we're going to study how you prepare a two particle state. And once you prepare the two particle state, then you can consider scattering. So as I said, primary state or ground state of the harmonic oscillator is just inserting a point at the origin of the y-plane, or if you want to map it to the cylinder, it would be Euclidean past. And you can put the point in any other position in the y-plane by just applying the translation operator to the ground state to create a single particle at any point and any angle. So a generic state, a generic single particle state would then look like a coherent state because of the harmonic algebra with the Gaussian wave function with the same width as the ground state, but center offset from the origin. Okay, so non-interacting two particle state actually is, of course, a tensor product of two coherent states defined above. Now we can split this into center of mass and separation of the particle wave function, because as we showed that our Hamiltonian, the Hamiltonian decouples and the Hilbert space decouples, and you can do this splitting. So by doing this, we can choose a state which kills the which is killed by the annihilation operator. This would be again a primary state wave function, center of mass wave function. So now the special conformal operator is a sum of two operators. So to get something with eigenvalue 0, we just need to choose this combination to be 0. And once we've done that, we got a state which is annihilated by a special conformal translation, a special conformal operator, and then we then got a primary state in our center of mass wave function. Okay. All this to say that the Euclidean scattering states, the states that we get by doing this Euclidean time evolution that we have described so far, would be a tensor product of a primary state in center of mass and a non-trivial wave function in a relative part. So here a dagger or creation operator built from the separation variable. So this is different from our big A dagger. And this is the term which would survive after fixing everything by symmetry. So now that we have prepared the particles via Euclidean time evolution, we can consider a scattering problem. So we consider the scattering problem by inserting a real, by inserting a real time evolution between the prepared initial and final states. This would the particle would start from far away, they go to the center, they would interact, and then they would again become decoupled. The Euclidean insertion, the Euclidean time evolution that we have tell us how the correlator would depend on ZZ bar. And this picture would actually give us a way to build a correlation function, which is actually which is equivalent to a flat space scattering. Yeah. So this picture is what you get from doing all these processes to build a flat space scattering. And this is a flat space scattering, which is equivalent to a correlator in the non-relativistic limit, of course. Okay. Okay, so now that we have seen the answer to the first question, let's approach the second question on how to extract data about the two particles in ADS. So as argued, any information about energy shift of the primary two particle states can be read from the relative Hamiltonian. This was argued in the conformal symmetry section. The non-relativistic potential for the two-body problem is then given as follows, where mu here is the reduced mass. Now we can use just effective quantum theory to obtain the energy shift of the two particles in ADS to a potential VR, which is much smaller than mu omega r squared. So basically, we find the eigenstates to the p squared 2 mu plus half mu omega r squared, and then we calculate the effect of VR perturbatively, and this works well when VR is much smaller than the other terms. And since the dilatation operator is the Hamiltonian, then this energy shift would give us the anomalous scaling dimension of the CFT. So with this procedure, we would be able to read the anomalous scaling dimension of the CFT. Okay. So in the next slide, I focus on calculating this energy phase shift, this energy shift for the special problem of Kepler. I wrote Coulomb potential on the subject and Kepler in the text because they're equivalent, and I wasn't able to choose which one, but it's just K over R potential. And then
Zahra,
yeah,
you have 10 minutes, around 5 + 5 left.
Okay, great. So we can now focus on the Kepler potential and basically do the sum that I showed in the previous slide, order by order. Here, because we have because our potential is linear in GN, we can just see that the terms in the sum would just give the anomalous dimension or the energy shift order by order. Each term would give the relevant order anomalous dimension. Okay. So in order to get the anomalous dimension, then what we are left to do is just this simple ADS integral, and then we would be able to get the anomalous dimension for any energy, for any N and L, which would be interesting because it's a data otherwise not so simple to achieve. Okay. If we do the calculation for gamma and L for the first integral, I don't bother writing the second integral here, but for the first integral, it can be written here. You're gonna get a 3F2 formula. Okay, this is not very illuminating, so let's just look at different limits. So flat space in the language of ADS-CFT would be large N, large L. We see that we can recover this log NL, which is the log of impact parameter. It would be proportional to, it's like the IR log that we get in the impact parameter space in the flat space time. So, okay, the flat space limit checks out. And then we can also look at the large L limit. In the large L limit, we would expect it to scale as square root of L, 1 over square root of L, which it does. This comes from the fact that the potential is 1 over R. So yeah, you can work out how this at large L, this would mean this. Okay. Okay, so with all of this analysis, you can actually get information about the CFT Regge trajectories, as I promised. Using the analysis I just described, you can get information for when V of R is small, which would basically be at the endpoints or wherever you can parametrically neglect V of R. At the bottom, you see that you can, for the bound states, which you have negative energy, you can have like a non-quantum mechanical big bound states solar system. For this system, we can actually get these trajectories by ignoring the by actually taking omega to 0. So going to flat space and asking V of R to dominate the ADS potential. Then at high energy, you have the Rutherford scattering, which again, this would be the leading contribution, and you would neglect omega contribution. You take omega to 0. Same for hydrogen atom, but for hydrogen atom, you of course have the quantum mechanical. Important. So this graph is something, for some part of it, we can only get it numerically. I have showed you how to get the end part, and also for some other parts in the positive energy analytically, but to understand this whole picture analytically, it's still an open question. Okay. I don't know if this is something which would be of interest for only CFD experts, so I will be very quick. Basically, what I'm trying to say is that the calculation that has been done in the bulk ADS perturbatively now has a nice interpretation in terms of the number of graviton exchange in the cross channel. So this in ADS CFD would correspond to exchange of a stress tensor operator and multi-twist operator of stress tensor in the CFD. And then we can use Lorentzian inversion formula developed by Simon to extract the scaling dimension and OPE coefficient of the operator in CFD, and check whether in the realm of the inversion formula, check whether the formula we get matches from what we get from the CFD. Yes, Lorentzian inversion formula is just an integral formula which have the data about a scaling dimension and OPE coefficient through its poles and residues. It has a dependence of the double disk of the correlator. In that sense, it's similar to the Frost-Argeribov formula, which extracts information about partial wave amplitude from the discontinuity of the amplitude. And we can actually check that for n equals 0. So remember, our result for all n was for all n and all L. But here, using inversion formula, in order to go from n equals 0 to n equals 1 to higher n, you have to do much more complicated calculation, and already going to n over 10 is very difficult. So that's nice that we have an all n result. But anyway, this can still be used to check. And then we can see for the leading anomalous dimension of the leading Regge trajectory, we actually get the same thing as what we had from the 3F2 formula. These are two very independent calculations. So I guess, yeah, it's interesting that it works out. Yeah, in the paper, we actually do it for n equal 1 as well for the subleading trajectory, but it's just more complicated. And there's no point in writing it out. Okay, so summary and outlook. So in this talk, we analyzed the non-relativistic two-body problem in ADS. Specifically, we have introduced a physical way to extract the flat space bulk asymmetrics from ADS CFD correspondence. I'm calling it a physical way because we got the states by just preparing the state. We prepared the states by doing a Euclidean time evolution. This has a few advantages compared to the construction available in the literature. So since we use Euclidean time evolution to prepare the states, we did not need to smear in and out states over real time, which introduced some difficulty. So this made us able to get the correlation function with the specific Z and Z bar dependence, and there was no smearing in the correlation function as well. And also, because we split the Hamiltonian as mass plus center of mass plus relative, where mass is larger, we didn't have to actually, except for the section that we did it perturbatively, but in principle, we don't have to treat the H relative, the relative Hamiltonian perturbatively, and the relative Hamiltonian can be strongly coupled. And because it's non-relativistic, it's a simple, strongly coupled system that we can approach using many techniques. This is as opposed to approaches that in order to introduce in and out state, they had to treat VFR as a small correction. Okay. As a first step to...
Zahra, you're running quite low on time, so...
Okay. Okay, so people can read it. And yeah. Yeah, so this is, we use perturbation theory to get information about double twist operators. And okay. These are the things that you can do for future direction. You can consider, yeah, okay, people can read it, and thank you. So, okay, let's have time for questions.
Yeah, no, I'm sure we have time for some questions. So if anybody has some questions, raise your hands. So I see Enrico already has. Please.
Hey, Sarah, thanks for the super nice talk.
Oh, thank you.
So as far as I understood, you're only using this relative potential. You're using the Newtonian potential because you're directly in non-relativistic limit. I mean, of course, you know, there's a lot of activity in like post-Newtonian in flat space. And since you also mentioned that you might be able to do strongly coupled Hamiltonians, do you see a way to go beyond the Newtonian order and then maybe do strongly coupled? So in a sense, like maybe can you do something like the probe limit of black hole in spirals, where we also have all orders in G Newton results? But it's not really non-relativistic because you have one probe particle. But maybe you can do still some hierarchy of scales M1, like delta 1 much smaller than delta 2, so that you can still approach some sort of probe limit where you do have like a flat space.
Okay.
A flat space, all orders in strongly coupled result.
Yeah. Okay. So let me ask. There were many. Yeah. There were a couple of questions, so let me ask them one by one. So in the non-relativistic limit, you can, of course, do like a post-Newtonian expansion. So you can, of course, I only consider GM over R. You can consider a higher order term, like a 1 over R squared terms, and I don't know, wish to get something like precession or other things of the orbit. This can be done in the context of this problem. You can also, and this can also be done perturbatively, like using the exact same method that I described. But in order to do like a strongly coupled VFR, strongly coupled relative Hamiltonian, you would, of course, not be able to use non-relativistic. You would not be able to use perturbative approach. But then there are many other things you can use. You can like use WKB approximation. Since the problem is not too difficult, you can, I don't know, maybe use numerical and things like that. These are all would fit in the picture of having the non-relativistic ADS CFD, like ADS and reading data. But the problem, it wouldn't quite fit though. So the problem that you would have to, so as I said, I would have, in order to go to the non-relativistic limit, I had all of my operator having a scaling dimension large. So I can't really have like a light particle. But I can have one particle much lighter the other one, but still all of my particles have to be non-relativistically moving. So they have to go slow enough. Yeah. So is that the setup that they have in the probe? You were saying that they are summing in GM. Oh, I see. Okay. So are they able to write a Hamiltonian which is resummed in GN for the probe limit? If that's the case, then yeah, okay, I see. Yeah, then you might be able to do it, having one particle much lighter than the other one, but still everything's moves. Everything needs to move non-relativistically. But if you want to have one particle moving fast compared, yeah, like of order C, then everything that I've spoke about would break down. So you still need
Thanks.
one. Yeah, but you can have, we actually do consider particles, like two particles with one mass is much smaller than the other. So probe limit in the NR limit.
Okay.
Question.
Yeah, very interesting stuff. Okay, well, maybe we should thank Zahra for a fascinating talk, and maybe ask Cliff Chung to start sharing his slides.
Thank you very much.